Welcome to Japan House, London, to our webinar. I'm Simon Wright. I am the Director of Programming here at Japan House, London. And welcome to our JAXA series and the first installment, which is searching for the origins of the universe. JAXA, of course, is the Japan Aerospace Exploration Agency. And we are delighted today to be able to be joined by two members of JAXA. We are Mr. Sudo Katsuya, who is the director of the Paris office of JAXA, and he's joining us from Paris. And Dr. Yoshikawa Makoto, who is the mission manager of the Havahusa2 project and associate professor of JAXA's Institute of Space and Astronautical Science. And he is joining us from Yokohama in Japan. Welcome, both of you. Thank you very much indeed. But today as well, we have Dr. Natalie Starkey, who thank you very much indeed for agreeing to chair today's event. Dr. Starkey is a science writer and science communicator with a research background in geology and planetary science. Her work on US, European, and Japanese space missions, such as Stardust, Rosetta, and Hayabusa, led her to writing her first book, Catching Stardust, Comets, Asteroids, and the Birth of the Solar System. She's currently working on her second book, Fire and Ice, The Volcanoes of the Solar System, and she is Public Engagement Officer for Physics at the Open University. Thank you very much indeed, Dr. Starkey, for agreeing to do today for us. I shall now hand over to you, if I may. Just before that, we will look at how people can watch this webinar. Please note that if you're joining us, your microphone and webcam will be disabled for the entire duration of the event. Please use the question and answer feature to type your questions for the speaker or hosts at any time throughout the session. If you do not want your name to be attached to your question, please check the send anonymously option. All questions will be collated by a moderator at Japan House London, and we hope to get through as many as we can. There will be an opportunity for your questions to be asked at the end of this session. Please note that the contents of this event will be streamed live on Facebook and YouTube, where a recording will be archived later. Thank you very much indeed. If I may hand over to you, Dr. Starkey, and we look forward to today's webinar. Thank you very much indeed.
Thank you, Simon. Hello, everybody, and welcome to this special event, Searching for the Origins of the Universe. As you've heard, I'm Natalie Starkey. I'm a science writer and space science communicator. Now, today we're going to be hearing from two people. The first is Mr. Sudo, who is working as the director of the Japan Aerospace Exploration Agency, that's otherwise known as JAXA, and he works in Paris. Now, he joined JAXA actually in 1995 when it was formerly the National Space Development Agency of Japan. Mr. Sudo is going to introduce us to the aims of JAXA, giving us an overview of their activities. Then we're going to hear from Dr. Yoshikawa, who is an associate professor at the Institute of Space and Astronautical Science. That's a division of JAXA. Dr. Yoshikawa is also mission manager of Havabusa2, as you've just heard, and this is the space mission we're going to be hearing in much more detail about today. Now, the timing of this event is perfect because Havabusa2 is set to return to Earth with samples of asteroid Ryūgū that it collected in space in just a couple of weeks' time. Now, this is only the second time that asteroid samples have actually been collected and brought back to Earth from space. Dr. Yoshikawa will introduce us to the mission, describing its activities since launch, its work on asteroid characterization and sample collection through to sample return. It's hoped that the samples returned to Earth will reveal key information about the formation of the objects within our solar system. So I look forward to putting your questions to our speakers later on in the event. But without further ado, I will let Mr. Sudo begin. Thank you.
Yes, thank you very much. Can you hear me well and see the screen well? Yes, shall we start? Good morning, everyone. My name is Katsuya Sudo. director of JAXA Paris office, and assigned on this year's August. And I am very honored to be able to introduce JAXA to all of you today. So I would have liked to speak to all of you in person, if possible, because it is very near here to London, But under these circumstances, it's difficult now. So first of all, I would like to wish you all, I wish under your important persons' health and safety. So today, I will briefly introduce JAXA and JAXA's activities at the beginning of the session. And then after that, Dr. Yoshikawa, a very famous Japanese researcher, will introduce the Havahusa2 mission, which is currently heading to Earth. His presentation is very, very exciting for me as well. The name of JAXA is becoming more and more famous in Japan, but it is still not well known worldwide. I don't like to say that this is like NASA in Japan, although it is often used. So when I was looking for an apartment in Paris this August, the real estate agent and the landlord were suspicious when I said JAXA. But as soon as I said Japanese NASA, like NASA, they rented an apartment to me. Again, I don't like this situation. I'd like to say that NASA is like JAXA. So let's move on the slide. So JAXA itself was established in 2003 through the merger of agencies specializing in space science, ISAS, aviation, and rocket and satellite development agency, NASDA. Although the history of JAXA is only less than 20 years, the history of Japan's space and aviation research and development is more than 60 years old. Japan's first satellite was launched in 1970. The world's first satellite launch was Sputnik 1 at the Soviet Union in 1957. The following year, the United States launched a satellite. But in fact, the third country in the world to launch an own satellite was the United Kingdom, named Ariel 1 in 1962. It was launched by US, but the third satellite in the world. Let's back on the introduction of JAXA, page 3. This slide shows the structure of Japan's aerospace policy make and implementation. Unlike the UK Space Agency, JAXA is not a purely governmental organization, but an implementing agency that is supervised by some governmental bodies. JAXA is supervised by the Cabinet Office policy and mixed research and development mainly. In addition, we also receive governmental supervision for communications and economic related ministries. Let's see page 4. This slide shows the structure from space policy to implementation in Japan. First of all, the head of strategic headquarters is a prime minister in Japan, but he was replaced this September. So I'll use this slide on page 5 to explain. The goal of Japan's space policy is as follows: space security, disaster management, space science and exploration, economic growth and innovation, and strengthen the competitiveness, like industrial and scientific and the technology basis. Under these goals, so we have a implementation plan revised annual basis. JAXA is carrying out its activities in accordance with this implementation plan. This page is the organization chart of JAXA. Please check the activities of each department. From the left side, space transportation. The next is space technology. It means satellite. The human space flight, space exploration. And next pillar is space and astronautical science. The next is aeronautical technology, research and development directorate. Strategic planning and management department pillars. And last is general affairs, including human resources procurement. This is JAXA organization chart. Next is budget. A large portion of the budget is allocated to rocket-related and International Space Station project, which account for 40% of the total. As you see, the next page, the budget tendency. The budget has been tight for the past few years, as you can see. Without a supplementary budget, the yellow line, we cannot keep it up, but we were trying to request 1.5 times as much to the Ministry of Finance for the next fiscal year, 2021. Especially for exploration-related budget, the results are not known yet. However, expectations are high for us. These are JAXA's field center. My office in Paris covers the whole of Europe area. So JAXA is the executing agency for many of these areas. After this, we will focus on one of these areas, planetary exploration, and introduce the hot topics, the Havabusa2 mission. So I will hand over the floor to Dr. Yoshikawa. Yoshikawa sensei, お願いします. Thank you so much.
Thank you so much, Mr. Suda. That was a perfect introduction to the JAXA activities. And I was amazed actually how far you go back in history with those first activities. I had no idea about that, so thank you for that. So we will hand over to Dr. Yoshikawa now. Are you ready to begin?
Yes, thank you. Okay, so good morning, everyone. My name is Makoto Yoshikawa, Mission Manager of Havabusa2. I'm very happy to talk about Havabusa2 today. So now I share my screen. And I show my slide. Okay, so this image, and this is a Havabusa2 spacecraft. So today I'm going to talk about this mission in detail. But first of all, I show this slide. This shows today's Ryūgū and Havabusa2. This figure shows the orbits of planets. This is Mercury, Venus, and this is the Earth, and this is Mars. And all small dots are asteroids. There are many asteroids. And one of them is Ryūgū, this pink dot. So, and Ryūgū, this asteroid Havabusa2 explored. So today, Ryūgū is very close to the Earth, here. And actually, distance between Earth and Ryūgū is about 15 million kilometers today. However, Havabusa2 is much closer than that. The distance between Earth and Havabusa2 is just 6.6 million kilometers. And Havabusa2 will come back to the Earth quite soon. Okay, so this explains Havabusa2 mission. Havabusa2 mission is the second asteroid sample return mission following Hayabusa. This left-hand illustration, this is the original Hayabusa. And the target asteroid of Havabusa2 is Ryūgū, which is C-type asteroid. this C-type is very important because we want to study organic matters on the asteroid. So our main objective is to study organic matter at the beginning of the solar system. Havabusa2 was launched in 2014, and it arrived at Ryūgū in 2018, and now it is on the way back to the Earth. The Earth return is 6 December 2020, this year, of course. Actually, this is a date in Japanese time. So in UK time, Earth return is 5th December. So this shows the purpose of Havabusa2, science of asteroid mission. So main purpose is to study origin and evolution of the solar system. As you may know, Earth, planets like Earth or asteroids were born 4.6 billion years ago from molecular cloud. And if we study the material on asteroids like Itokawa or Ryūgū, we can study the original material that formed two planets. And especially Ryūgū, which is C-type asteroid, Ryūgū has the organic matter. Organic matter, it is 4.6 billion years ago. I mean, organic matter before Earth's life. So if we study organic matter, maybe we can understand the origin of life on the Earth. So this is our main purpose. And this shows the Havabusa2 spacecraft. It is not so big. The body size is just 1 meter by 1.6 meter by 1.25 meters, very small. And the total mass, including fuel, is just about 600 kilograms. But it has many payloads. So these are the science instruments. ONC is an optical navigation camera, and the LiDAR is a laser altimeter, and the MU3, this is a near-infrared spectrometer, and the TIR, this is a thermal infrared imager. So these four science instruments. And Havabusa2 has also 4 lander and small rovers like this. Mascot, which was made by DLR and CNES, Germany and France. This is a small lander. And these 3, Minerva 2, these are very small rovers. So Havabusa2 has many equipment to study asteroid Ryūgū. So now I show you this slide. This summary of mission scenario of Havabusa2. It was launched December 3rd, 2014, and just 1 year later, it came back to the Earth to perform Earth swing-by. This Earth swing-by was successful, and its orbit was changed to go to the Ryūgū. And Ryūgū arrival was June 27th, 2018. And after this, we had many experiments. For example, the first one is small lander, small rover, Minerva 2 release. And next is a mascot release. And then first touchdown was executed in February 2019. And then we executed impact experiment to make the small crater on the surface of Ryūgū. And then we did second touchdown in July 2019. And after that, we made another experiment. We Havabusa2 separated 2 target markers and 1 more small rover into the orbit around the Ryūgū. So we made these 3 objects actual satellite around the Ryūgū. And Havabusa2 left Ryūgū in November 13 last year, and now it is on the way back to the Earth. So, but I think it is better to show movie. This is a computer graphics of Havabusa2 exploration. So at first, it starts from the arrival at Ryūgū. This is arrival. And after this, we observed Ryūgū in detail, and then we released 2 small rovers nearby to 1, like this. The altitude is about 55 meters, and they slowly went down to the surface like this, and bounced like this, and landing. And actually, they can hop like this. And by moving like this, they took images of the surface of Ryūgū, and they measured the temperature. And then we released mascot small lander like this. This was also successful, and mascot took a lot of scientific data on the surface of Ryūgū. Okay, so the next thing is a touchdown. This is very difficult because the surface of Ryūgū was covered by a lot of boulders, lot of large rocks. So at first, we released these small things we call target marker. This is an artificial landmark when it will be used when spacecraft makes touchdown. But this time, we released only target marker, and the spacecraft did not touch down, but it went up. But you can see target markers here, and the spacecraft moved by watching target marker. And the touchdown is like this. So yes, so from the altitude of about 8.5 meters, looking at the target marker, it moved quite precisely, and it will make touchdown. This red line indicates the laser light. Okay, so this is a touchdown. Actually, the speed is very slow. And this is a sampler horn. When sampler horns touch the surface, small projectile was fired, and we think we got the sample of the surface of Ryūgū. So the first touchdown was quite successful. And next thing is a very challenging one. Next thing is impact experiment. Yes. So spacecraft went down to about 500 meters high and released this box. This is the impactor. And impact 30 minutes later. So spacecraft quickly moves and hide behind the asteroid. Okay, because we want to avoid the debris from the impactor. But before hiding, we released this small camera we call DCAM, separation camera, to watch the impact event. Okay, so spacecraft hides and then explode, impact, and this small camera can watch the impact event. Okay, so still movie continues, but maybe it's better to stop here. And after this, we did the second touchdown. So now I show you a real image. At first, this is the first image of Ryūgū. It was just a point, this small dot. This is the first image that Havabusa2 took, but just a point. And then this is this shows the approaching Ryūgū. So the Ryūgū became larger and larger, and you can see its shape. And we are very surprised to see the shape was like this. It is a spinning top shape. We never imagined such shape before. But anyway, the arrival was successful, so we are very happy. This photo was taken in the operation room. All of us were very happy, and actually I am here. This is me. So this is a Ryūgū, a very interesting asteroid. The shape is interesting, and also we found that there are no wide, smooth area on the surface. All the surface were covered by these rocks. So this is very interesting, but the touchdown, the landing is very difficult because we couldn't find large flat area. But anyway, we continue science observation, and we took a lot of data. We estimated very precise shape model, and this is a color image. Actually, the real color of Ryūgū is very dark, very black. And this is a temperature observation, and this is a gravity. And the right-hand side, this is a spectrum of Ryūgū. And actually, this is very important. The Ryūgū data is this black line, and you can see small dip here. This means that the surface material Ryūgū contains some water. So this is very important data. And this is a very amazing photo. They were taken by a small rover, Untitled these are the surface of Ryūgū. And right-hand image, you can see the motion of the sun seen from the surface of Ryūgū. And this is a result mascot. The mascot took very nice data, and we could know the surface rocks in detail. So the next thing is touchdown. As I said before, touchdown was quite difficult because we couldn't find a good area. At first, we chose this L08 area, because we thought this area has less boulders. But actually, this area was also covered by lots of boulders, lots of rocks. So we chose this small area, this one, 20-meter diameter. So we chose this area for touchdown, and we dropped the target marker, artificial landmark. However, the target marker dropped 5 meters from this area, this point. So there were two possibilities. One is this red area, the other one is this green area. And after lots of discussion, finally, we chose this area for the first touchdown. Very small, just a 6-meter diameter area. This size is similar to the size of spacecraft. But this area is quite close to target marker, so we thought this is better than the other. And this shows the first touchdown operation. Spacecraft went down to the altitude of 45 meters and make hovering and detect the target marker, and then down again to the 8.5 meters. And finally, free fall and touchdown and go up. So now I show you a real image. Please look at this right-hand image. This is a movie of first touchdown. So this dark one, this is a sampler home. And now going down, and soon sampler horn touches the surface of Ryūgū. Yes, quite soon. Yes, this one. So after a touchdown, we can see lots of rocks blown up. We also surprised to see this image. But touchdown was quite successful, and now too many people get together in our operation room. Okay, so the next is our challenge impact experiment. So as I said before, spacecraft went down to here and separate impactor. But before impactor explodes, spacecraft quickly moves like this and hides behind the asteroid. But before that, we separate this small camera, DCAM3. Okay, so now I show you real image. So this is a impactor. Yes, this one. So impactor is now going down. And then this is a impact. This is a moment of impact. So you can see ejector like this. And I have movie too here. So we can see how the crater was formed. So after this, this experiment, the spacecraft went back to this crater. And this is a photo of the crater. So left is a before impact, middle is after impact, and right is a comparison. So you can see clearly that we were able to make a crater. And the size is about 15 meters in diameter. So next thing is whether we should do a second touchdown. Actually, the purpose of making crater is to get the subsurface material. And however, inside crater is very dangerous, very risky for touchdown. So we study near the crater, and we found one location here. Here we found the material from crater were accumulated. So we chose this area for the second touchdown. But as you can see, there are lots of rocks around here. So we were very careful we must be very careful when we make touchdown here. And this is the second touchdown movie. Actually, the speed is very slow. This is 10 times faster than real speed. But anyway, you can see the touchdown like this. Yes. So again, second touchdown was successful. And accuracy of navigation was just 60 centimeters. I mean, the error was just 60 centimeters. We can do very, we could do very highly accurate navigation. And then we made extra experiment that is artificial. This was also successful. So now Havahusa2 is on the orbit coming back to the Earth, and now we are in the last part. Now we are re-entry terminal guidance. So now I show you this part in detail. This one. So we need several TCM. TCM means trajectory correction maneuver. So up to now, we finished TCM2. And the most important TCM is TCM3. If we carry out TCM3, spacecraft orbit change that collide to the Earth. So TCM3 will be done next week, November 26th. And just half day before re-entry, spacecraft release the re-entry capsule. And after releasing the capsule, the spacecraft carry out TCM-5 to avoid collision. And Havabusa2 will go another mission. Okay, so this is a destination of return of Havabusa2 capsule. This is Umera desert in Australia. So now many project member is in Australia to get the re-entry capsule. Okay, so maybe my time is nearly over. So this is a re-entry capsule operation, and we do hope that we can get the capsule, and after getting capsule, we bring it back to Japan and open it. Then we will know how much sample we were able to get. Okay, maybe the time is quite short, and actually I want to talk about the science, but I don't have enough time. So now we have a lot of science paper. This is a science journal paper, and now we know a lot of things about Ryūgū. And most important thing is its density. The Ryūgū density is just 1.19 gram per cubic centimeter, very small. So we think the Ryūgū, the structure of Ryūgū is a rubber pile. It is not a hard solid, but it's a rubber pile. Okay, so this is my summary. We think these small bodies are very important, not only for science, but also for space guard and planetary defense. Or it is also important for, in future, for resource or manned mission. So we think small bodies is very important. So that's why we are studying these small bodies. So this is the final slide. We did many world first by Havabusa2 mission, but still we have one more mission, which is return to the Earth. So Havabusa2 will return to the Earth quite soon, and if we get the sample, the next thing, a new science will start. Okay, thank you very much for your kind attention.
Thank you so much, Dr. Yoshikawa, and to both our speakers for those really insightful presentations. I think you'll all agree, or the people watching at home, that JAXA is doing phenomenal work. The idea of sending little spacecraft millions of kilometers away to repeatedly touch down on a small space rock is just absolutely fascinating to me. And it's a field that I've been involved in for quite a long time, and I'm still fascinated that actually these things are possible. It's not only that, but actually bringing back samples to Earth. I can't stress enough how important that is for space science. Having real samples from space rocks is so important for us to be able to understand how these objects are formed. And I always like to remember space exploration reminds us to expect the unexpected. Before JAXA got to the asteroid, they had really no idea what to expect. The problem is these objects are very small and they're very dark, as Dr. Yoshikawa mentioned. That's because they've got a lot of organic matter in them. And this is very dark. That's not life, I should stress. Organic matter is the building blocks for life. But this is why we think asteroids are so important to study, because they may tell us about how life got started on Earth and possibly in other planets in the solar system. So spacecraft need to be designed to cope with a range of unknown conditions. And then it's just amazing that when they get to these objects in space, millions of kilometers away, they're able to do such fantastic science. So that's actually kind of one of the questions I wanted to ask you about, Dr. Yoshikawa. How did you actually choose the target asteroid? Because we showed that image earlier in your talk where there's so many asteroids out there. So how do you finally choose one that you want to study in detail?
Yes, thank you. So, first mission, Hayabusa. Hayabusa explored Itokawa, which was S-type asteroid. So we want to study C-type asteroid this time. So we look for C-type asteroid, and of course, the first condition is we must choose the asteroid that spacecraft can reach and go and back to the Earth. Okay. First condition is the asteroids should be that spacecraft can reach. So then we found about 20 asteroids for candidate. But among 20 asteroids, C-type asteroid was only one, Ryūgū. So we chose Ryūgū.
Okay, that makes perfect sense. So in relation to that, I also saw that the asteroid was had a 50% porosity, you mentioned. So if this is right, it means there's 50% air or space air, whatever that might be in space. Now, this is incredible because we think of asteroids as a solid rock often. I think, you know, when they're portrayed in the Hollywood movies, we think of them as very hard, solid objects. But actually describing this asteroid as a rubble pile is really good because actually it shows us that it's not very well held together. People might be wondering, we often hear about asteroids on collision courses with planets. So what would happen if this asteroid were actually to be on a collision course with Earth, for example?
Yes, so of course we want to avoid the collision to the Earth. So one possibility is that we launch spacecraft and hit the asteroid. Then the orbit of the asteroid can be changed a little, only a little. So if the collision to the Earth is, for example, 20 years later, then small change of orbit will become large, and we can avoid the collision to the Earth. Do you understand?
Yes, thank you. So obviously I will stress again to anyone watching that we don't expect this asteroid to be colliding with the planet, so we should be safe, but obviously it is something we need to think about in general because we do have these objects orbiting around the solar system, and at some point in the future we do expect one, it could be much smaller than this, to be on a collision course with Earth. And this is of course how we get a lot of our space samples on Earth in the form of meteorites, which are simply space rocks that obviously land on the surface of the planet, and we can pick those up and study them. And these are basically the main samples we have from space on Earth. So actually going out to an object like you've done and bringing back samples is really special because we get to compare those two samples to each other. Right, I think I've got one more question for you, and it was related to really what's happening next. So having worked in space science, I understand it's a very international community. And as you mentioned that actually there's some European built instruments on the spacecraft itself. So what happens to the samples? Hopefully you're going to open up the capsule and find that you've got a load of sample in there to start studying. Are the first analysis done in Japan and then opened up to the international community, or is it going straight out there?
Yes, so if we open it in Japan, and at first we check the sample, and at first sample will be analyzed by our team, but I think 1 year later we will distribute the sample to worldwide. Okay.
Okay, and I have a question that's come in from someone who's watching. They're actually asking, what do the samples look like? What kind of materials are we expecting to find in these samples that have been collected?
Yes, this is a very good question, and actually we want to know it. And yes, but we expect that we will find organic matters like amino acid. So then we can study the origin of life.
And that's an important subject as well, because people probably aren't aware. It's something that I discovered once I got into space science, that actually we have detected amino acids in space in terms of space rock samples. There's meteorites contain a lot of amino acids, and they've also been detected in a spacecraft that went to a comet. And twice actually we've detected amino acids in space. So they're incredibly common throughout space. And what now, I guess what you're trying to do is look at the link between the amino acids that exist on space objects and what we have here on our planet that's eventually led to the evolution of life here. So it's a really hot topic, and I'm really excited that you're going to be able to start looking into this with, hopefully, with those samples that you've got. Another question coming in from the public, it's from Adam, and he says, is it possible for the samples to be damaged or contaminated once they return to Earth?
The question means when capsule goes down to the surface of Earth?
I think they mean once the samples are returned to the planet. Is there, basically what do we do to determine that they're not going to be contaminated with earth bugs and things like that?
Actually, we are very carefully, we treat sample very carefully, so no contamination will occur.
So this involves clean labs. I mean, I've worked in clean labs myself, and when I've had to go in, I have to, you have a hairnet and a mask, and you put a full suit on and gloves. And that's obviously a very important aspect of analysing these samples, because if we find amino acids in the samples, we want to be absolutely sure that they came from the asteroid and not from something that we introduced. So yeah, the protocols in terms of analysis are extremely high. And so yes, that's good to know. A really good question actually, which is something I was wondering. What's the time delay between, I guess when you were at the asteroid, first of all, what's the time delay between the instructions that you were sending from Earth and getting back information from the spacecraft?
Yes, so when touchdown was occurred, the distance from the Earth was about 2 AU. So the time delay was about more than 30 minutes going back. I mean, if we send commands, and we must wait about more than 30 minutes to receive the answer.
Okay, so that's a frustrating amount of time. I guess you have to sit very patiently and wait. And so just to re-emphasize, 2 AU is, so 1 AU is the distance from the Earth to the Sun, which is quite an incredible distance. Is it, I'm going to get the number wrong, is it 150 million kilometers? Is that correct? Or 93? I never remember this number in my head. Is that something around that number? So 2 AU is a huge distance that we're talking about. And I think that's an important point to stress in space science. The distances are huge to get to these objects. So you mentioned the Earth flyby that you did, where after launch to get out to the orbit of Ryūgū. And obviously that's necessary because we can't just launch from Earth and go directly in a straight line to the objects we're trying to get to. We've got to go on the orbital dynamics to get out there. So actually doing gravity assist, flying past a planet, and we can use Mars as well, gives us extra gravitational energy to get to the correct orbit we're trying to go on. I actually have a question from the public for Mr. Sudo now. It's actually related to JAXA's work in this area and how it compares to the work being done by other space agencies. Are you able to comment a little bit on that?
The collaboration, it means the collaboration of the other space agencies.
Yeah.
Yes. Of course, we have a lot of international cooperation. And so the first of all, I mentioned the successful of the launch of the commercial human space flight Crew Dragon, SpaceX, last Monday. Then so astronaut Noguchi-san start to the long duration stay, the international space like that. So we are, of course, a lot of collaboration, the international relations to the other agencies.
And I probably mentioned there's a very similar sounding mission that NASA are running called OSIRIS-REx at the moment. I think they're due to return to Earth with their samples a little bit later than you.
Sample.
Yeah, so are you going to be discussing the work that you've done with them? Because obviously you're a little bit ahead of them here, and they've gone to a very similar looking asteroid, but one that was quite a bit smaller. So yeah, how much are you in contact with NASA and their teams on that mission?
So Yoshikawa-sensei can answer this question.
Yes, actually, we have very nice collaboration with the team of OSIRIS-REx, and we have many discussions before touchdown. And actually, their OSIRIS-REx touchdown was quite successful, and but before that, they asked me many questions about the Havabusa2 touchdown. Anyway, we have very nice collaboration, and actually, we will exchange the sample too in future.
Excellent. And it's important to point out that this is a really important point about space science and exploration in space. It's a very incremental process. Obviously, you had the Havabusa mission, Havabusa1, should we call it, and you learned a lot from that mission that fed into this one and how you were going to do the sampling. And I guess everyone's learning from those experiences. Moving forward, this is a question for either of you. What are the future plans in terms of missions to asteroids or comets or other planets that you'll be able to use your experience of Havabusa2 for?
Yes, at first, we are now planning extended mission of Havabusa2 because the spacecraft Havabusa2 is very healthy, and actually we have a lot of fuels, still a lot of fuels. So now we chose one very small asteroid for the future, for the extended mission. It doesn't have name yet, but very small. The size is about 30 meters in diameter. And spin rotation period is just 10 minutes. So small and very fast rotating object we chose. So this is an extended mission Havabusa2. And in JAXA, we have another very big mission, which is called MMX. MMX means the MMX mission is Mars satellite sample return. So spacecraft will go to Phobos and get the surface material and come back to the Earth. This is the next JAXA sample return mission.
And Phobos is, that's one of the moons of Mars, is that correct?
Yes, moons of Mars.
Yeah, okay. So what are we hoping to learn from that? And why are we going to a moon and not Mars itself?
Yes, I think both. Yes, we want to know the origin of Mars itself. Also, we want to know the origin of Mars moon too.
Do we know much about that moon at the moment? Is it thought to be a captured asteroid?
Yes, somebody said the moons of Mars are captured asteroid, but others said it was formed by big collision to Mars.
Okay, so I guess by going there, we get to explore these objects and actually hopefully answer these questions. And you've got obviously a lot of experience now in touching down on such objects. So I'm looking forward to learning more about that. There is another question coming in from one of our viewers to Mr. Sodu. Sorry, I keep on getting your name wrong, Sudo.
Okay.
And you mentioned the budget issues. So the question relates to whether private industry has any role in supporting these missions.
Yes, I mentioned we are requesting the 1.5 times as much next fiscal year, and also we are collaborating with public partnership like that. Then but for the science field, we are using our original budget within JAXA. But for the exploration to the moon and Mars and beyond, we are collaborating with industries. We will be collaborating the industries in the future, I think.
Okay, thank you. Let me see. I'm just going to check if I've missed any questions that have come in. I think we've covered most of those subjects. Hello, Simon. You're back on. This must signal that we're nearing the end, unfortunately. I feel we've answered lots and lots of questions today.
We have had wonderful, wonderful questions indeed. Thank you very much indeed. In fact, there's one that I've seen that's come through. If I may just cheekily ask at the end, Sudo-san and Yoshikawa Sensei, are there any apprentice opportunities at JAXA? We've had one from our viewers who would like to understand whether it's possible to work at JAXA. Sudo-san?
Excuse me, what do you mean?
How do we apply to work at
work in JAXA? Okay. So I think that the inviting researcher, something like that, in the 5 years or so, it's always open, especially the science field. Therefore, could you please check the website regularly? So sometimes open for the scientists, especially.
Oh, wonderful! Thank you very much. That is great. That is unfortunately all we have time for today. I have to say, it was a marvelous set of presentations. Thank you so much indeed. In fact, we've got one last question here from Mariam, who's asking whether we will be holding more talks like this. And Mariam, I will be able to say that yes, indeed, this is only the first in a series of talks with our colleagues at JAXA, to whom we are extraordinarily grateful for agreeing to work with us on that. So thank you so much. Thank you very much, Mr. Sudo, who has joined us from Paris. Thank you very much indeed. We look forward to continuing to work with you. And also Dr. Yoshikawa, thank you so much for joining us from Yokohama in Japan today, and for a marvelously interesting and informative presentation about Havabusa2. I wish its return the greatest success in the coming weeks. Thank you very much, Dr. Starkey, for agreeing to chair this. That was wonderful. I hope you've enjoyed it as much as we have.
I have immensely. Thanks very much for inviting me.
Not at all. Thank you very much indeed. So please do look out for these next events. I think we have a slide which will show that. Yes, indeed. So early next year in 2020, we will be having more looking at topics such as Earth observation satellites and developments in Japanese launch vehicles for JAXA's space exploration missions. Please do check our website for details, and also on social media. Just a couple of notes from Japan House. We don't always or only look at space. If you've only just joined us for the first time, we have an exhibition at the moment, which unfortunately, due to lockdown rules in London, means it is temporarily closed, but that is Architecture for Dogs. It is due to reopen, all things being well, on the 3rd of December. Please do check our website for details there as well. We also have some exciting events coming up. We have an online talk on the Japanese diplomat Sugihara Chiune, who helped thousands of Jewish refugees flee Europe during World War II by issuing transit visas to Japan while working at the Japanese consulate in Kaunas in Lithuania. And this marks the 80th anniversary of the issuing of these visas for life. And we also have another first in a series, and this is about Mashiko. This Mashiko is the ceramics town in Tochigi Prefecture in Japan. And this event celebrates 100 years since the founding of the Leach Pottery in St. Ives in Cornwall, with a panel discussion exploring the contributions of those founders, Hamada Shoji and Bernard Leach, in who both forged the shape of Japanese and British studio pottery. A very brief look at what's happening in January, all being well. After our exhibition finishes on the 6th of February, we should be starting a new exhibition all about textile innovation from Japan. thank you very much once again. Thank you very much, Dr. Yoshikawa. Thank you very much, Mr. Suda, and thank you very much, Dr. Starkey. I look forward to our next presentation about JAXA. And in the meantime, I hope everybody stays safe. Thank you very much indeed. And we look forward to seeing you again. Thank you very much. Thank you. Please stay safe. Goodbye. Bye-bye. Thank you very much.